So now we want to consider how to pick up a specific attribute of the data and apply some criteria of the attribute so to group the training samples into different subgroups and make a node in the decision tree. The principle of this operation is to pick up an attribute that if we subgroup the samples, we gain most information about the target values. If you consider the machine learning models or whatever predictive mechanism you can build from a set of examples, though in essential that is to transform information from one format to another. The source format of the information is the X part of the data, the part that could be observed both in the training samples and when we deploy the model we built in practice. And the target form of the information is, of course, the target values, those whatever we want to predict. This format of information, we cannot observe this format of information when we deploy the model. So the transform of information from the observable part to the non-observable target part is a job done by the model. Look, there is no free lunch. Our model cannot create information from nothing. All the information must be contained in the observable part so that the model can do predictions according to that, and that is the underlying principle of statistical learning or learning from example data. Any machine learning methodology, including decision trees, adopt the principle of information transformation, implicitly or explicitly. In particular, in decision trees, if we think about the construction operations, that can be think as we ask questions with respect to or questions that can be answered using the observable part of the data, and using the answer we got from those questions to clarify our knowledge about the target domain, the target value of the data. An obvious question rises is that if we want to measure how much information we can gain by asking questions and getting answers about the observable part, we need the measurement of how much information we have about the target value before and after asking the question. So in general, we need some mechanism, we need some measurement about the information of some uncertain situation. The concept we want to introduce, entropy, here is the measurement of information. The idea comes from physics, in particular thermodynamics, is to measure the distribution of a large quantity of particles and see how chaos contained in that population. In information theory, entropy played a similar role. It is a measurement of, in this sense, we might call it a counter-measurement about information on an uncertain situation. To be clear, the unit of information is in bit or bits. that is the expected number of yes or no, those binary answers one needs to get to completely clarify any uncertainty about a situation. I have repeatedly used a term situation without explicitly defining it. Okay, that is not rigid. To be more specific, a situation means some interested quantity, that of stochastic nature. For example, in our previous example of the iris dataset, the particular quantity we are interested in is the species of those flowers. And in all the datasets we have dealt with this quantity, the species of flowers can take 3 different kinds of values. And given a sample, all 3 different kinds of values can happen with some probability or in some proportion. Consider a counterexample. If for another set of the same iris flowers, but for this set, we know ahead that all the flowers were collected from a certain region, and only one of the 3 species can distribute in that particular region. So in this situation, although we are also concerned with the same target quantity, but by the knowledge of the region of those samples, all the uncertainty has been eliminated. There is no information we are interested about in this situation, because without asking any questions about the flowers, their physical attributes or whatsoever observable parts, we even do not need any observation and can be sure about the species of those flowers. Of course, given that our prior knowledge is accurate that only one kind of one species of the orchid flower can distribute in this region. In this certain case, if we force an entropy in this situation, the entropy should be 0, because we expect to have 0 answers of the observable part of the data to completely make clear what is the answer about the interested quantity, the interested value that is a species. Okay, let's check the formal definition of entropy. If we elaborate the equation carefully, we can find 3 parts in this equation. The summation goes over all different possible outcomes of the stochastic event, the probability of different kind of events, P. So we give P a subscript I represent different events to distinguish different events. This probability is used to calculate the expected value. The third part, the log inverse probability, seems to be most complicated. Now we start understanding the equation from this term, the inverse probabilities logarithm. This term represents the minimum number of smart questions to ask to clarify the situation in the population represented by P or Pi. By smart, we mean that the optimal way of asking yes, no, or binary questions, so to eliminate uncertainty in the situation. Let us see an example. In this example, we consider an event that has a probability of 1 over 8. That is 12% 5% to be the outcome. And to imagine such an event, consider you have a V8 engine, but someday you find your car runs not as powerfully as normal, and you can hear funny noises from your engine. You judge perhaps one of the cylinders is misfiring, and the task now is to find out which cylinder is at fault. Also, let us say that your car performed perfectly previously, so we do not have any prior knowledge about which cylinder is most likely to be the problematic one, and each of them has the chance of 1/8 to be our target. Also, let us give the problem some practical relevance. Say, the problem only appears when the engine is running cold. So for each test, you need to wait approximately 15 minutes for the engine to cool down. So this gives the finding the answer of each test a time cost of 15 minutes, which can serve as kind of incentive for us to minimize the number of the answers we need to seek. A straightforward solution is, of course, to test the cylinders one by another, and you don't need to be an expert in probability to estimate the cost or the number of questions on average we need to find by employing this scheme. If we are lucky, we may encounter the faulty cylinder in the first trial. If we are not, we may keep trying and we encounter the cylinder in the second trial, also with a chance of 1/8, and maybe in the third trial with a chance of another 1/8, so on and so forth. If we are extremely unlucky, we may encounter the cylinder in the 7th trial. And also, after the 7th trial, we do not need to try again if we still haven't found the problematic one. The last one must be the one at fault. So totally, we are looking at an average number of answers or tests to be 1 plus 2 plus 3, go on and until arrive plus 7 and plus another 7. The two sevens correspond to we encounter the 7th cylinder to be the problematic one, or the last one is the one we are finding. So totally, the average number of questions we need to ask is 4.3 something. But as many of us may have already figured out, we can obviously do better than that trivial scheme of testing cylinders one by another. For example, we can simultaneously disconnect the first half of the cylinders and to see if the funny noise disappears or not. And after locking the problem in half of the cylinders, we can again test half of the remaining cylinders to see where the problem is. And again, in the third round, we must be able to locate the problem. In this way, no matter which cylinder might be at fault, we can find the problem within 3 tests. This example shows us with 3 questions, one will be able to eliminate all uncertainties in a group of events, each of which has a probability of 1/8 of happening. The number 3 corresponds exactly to the logarithm based on 2 of the inverse of the probability of 1/8. And that correspondence is not coincident. That is because using each of the question, we will be able to, let's say it informally, we'll be able to chop off half of the uncertainty from the situation. So after 3 chops, we will be forced into a region takes 1/8 of the original stochastic space. So informally speaking, now we arrive at certainty because we have chopped off the 7/8 of the uncertainty from the space. So now let us remember, if some event has a probability of P of happening, to describe such an event, we would need log based on 2 inverse P, this number of binary questions to fully specify the situation with respect to this event. And we call this number bits. The other 2 elements in the definition of entropy is to look after all different kinds of events that are events with different probabilities of happening, and weight the number of bits with respect we need to describe each of those events using their respective probability of happening, and summing up all those weighted bits. And now we arrived at an expected number of bits we need to use to describe or fully specify the entire stochastic situation or random situation. The larger number of bits we need to describe a situation, the more chaos the situation is in. So entropy is a measurement of the information or the lack of it about some random event, some random process. One property of this quantity of entropy mathematically, which I won't elaborate but I want to mention here, is that the more even those different events are distributed, the large entropy the entire stochastic process will have. For example, if all random events has exactly same probability, that is, actually we do not need to add those items one by one and by another together. We just need to calculate those logarithm based on 2 and 1 over some probability. In this case, the entropy will arrive at its maximum number given a certain number of events to be considered. For example, if we consider 2 events, the entropy reaches the maximum when the 2 events has equal chance of happening, that is one half. It is easily understood because when the stochastic events are even mixture and one do not have a predominant over others. From the observer's point of view, one has least information about the situation, and there is a maximum quantity of chaos in such kind of situation, needs a maximum number of bits to describe. On the other hand, consider another extreme. If we in ahead in prior know that some event of the event sets must happen with certainty, and all the other events has zero chance of being of happening. In this case, actually, we do not need a single bit to describe the entropy, and as we mentioned previously, the entropy or the chaos measure is zero for such situation. So that will give us a motivation that in classification problems, the way classifier do the work the classifier do is to use the information from the observable part of the data to push the distribution of the target value into some kind of purity. The distribution of target value could be the less bits of information we need to further clarify the target values, and the closer we are at the answer of the classification problem. That is the principle of building decision trees.